Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. Electronegativity and bond polarity. So another new concept within the OCR A Chemistry A-level specification is that of electronegativity, which is a measure of the ability of a particular atom to attract an electron pair from within a covalent bond. Now, Linus Pauling, famous chemist, Nobel Prize-winning chemist, produced a table of electronegativity values, which is given that label N subscript P. For example, sodium he evaluated at 0.9, hydrogen 2.1, chlorine 3, and fluorine 4.0. So of those four, fluorine is the most electronegative, and also within the periodic table we find that fluorine is the most electronegative element. Now, across the periodic table we find fluorine at the top right hand side, up here. And there's a general trend as you proceed towards fluorine diagonally across the periodic table like so, the electronegativity value increases. So the least electronegative element is francium, the most electronegative element is fluorine. As the position of the element in the periodic table approaches fluorine, the more electronegative you can regard it as being. So electronegativity is used to explain the phenomenon of bond polarity. So if we look at hydrogen chloride, got a covalent bond between a hydrogen atom and a chlorine atom. The atoms do differ in electronegativity. The hydrogen 2.1, chlorine 3.0. So what that means is that the electrons in the covalent bond are pulled more strongly towards the chlorine than towards the hydrogen. So if we look at what that means in terms of electron density, we could represent the polarity of the bond by showing that there is a greater electron density at the chlorine end than at the hydrogen end. But most commonly, we use a delta plus and delta minus symbol to indicate that hydrogen is less electronegative than chlorine, so more electron density is pulled towards the chlorine than towards the hydrogen. So we would mark that on a diagram of the molecule as hydrogen delta plus, chlorine delta minus. And we refer to these as partial charges. And they're opposite and are called dipoles. So a simple task, could you assign bond polarities to these covalent bonds by reference to position in the periodic table? Pause the lesson and resume when you have done so. So nitrogen is more electronegative than hydrogen, because nitrogen is much closer to fluorine than hydrogen in the periodic table. So delta minus for nitrogen, delta plus for hydrogen. If we look at chlorine and fluorine, well, chlorine can't be closer to fluorine than fluorine itself. So fluorine is more electronegative than chlorine, so delta plus, delta minus, as I have drawn here. But when you've got two atoms exactly the same, obviously their electronegativities are the same, and the bond has no polarity. So we would refer to the nitrogen-hydrogen bond as polarized, containing a dipole. The chlorine-fluorine bond is polarized, containing a dipole, but the hydrogen-hydrogen bond is non-polar. In pre-A-level chemistry, you're most likely told that there's two types of bonding between elements, ionic and covalent. It's either covalent or it's ionic. In fact, at A-level you are expected to appreciate that there's a continuum. There are degrees of covalent bonding and degrees of ionic bonding called covalent character, ionic character. For a perfect ionic model, the charge between the two ions are completely separate. So we have a positive ion and a negative ion. There is no shared electron space at all. For a perfect covalent model, for instance, the hydrogen molecule, there's no charge separation at all. There's no bond polarity. However, we've seen now, using the concept of electronegativity, that a covalent molecule such as hydrogen chloride in fact has some degree of ionic character in that the bond is polarized. Hydrogen delta plus, chlorine delta minus. And you will see when you look at ionic bonding in more detail that perfect ionic bonding is seldom found. Most ionic compounds tend to have some degree of covalent character, some small extent of electron sharing. For instance, sodium chloride. Now, the way to determine whether a compound will bond ionically or covalently, or in a covalently polarized fashion, or ionically with covalent character, is by using the concept of electronegativity difference. Where there's no electronegativity difference, for instance two hydrogen atoms, then that's the perfect covalent model. Where there is very high electronegativity difference, then charge separation might be considered complete. Potassium fluoride. But for most compounds, the electronegativity difference will tend to produce some intermediate type of bonding. So for hydrogen chloride, it's covalent, but polarized covalent. For sodium chloride, it's ionic, but with some covalent character. Now, to apply the idea of polarity not just to bonds, but to molecules, you must be fluent in the chemistry of the shapes of molecules. So if you are not, you need to refer to my lesson on shapes of molecules. If you are, we're going to proceed. We're going to look at methane, CH4. Now, methane contains carbon and hydrogen bonded together covalently. There is a bond polarity due to a small electronegativity difference between carbon and hydrogen. But we also need to take into account that the methane molecule CH4 is tetrahedral in shape. So if I produce a diagram of that molecule, you will see with the bond polarities or dipoles marked in that hydrogen delta plus on the right hand side is balanced by a hydrogen delta plus on the left. Hydrogen delta plus above is balanced by hydrogen delta plus below. So we would say that the charge distribution is balanced and the dipoles cancel. We would conclude that although there is some bond polarity, overall the molecule is non-polar. The argument being that the dipoles within the molecule cancel. Let's consider, in contrast, the water molecule. Again, we've got oxygen and hydrogen. There's an electronegativity difference, so each bond is polarized, and the molecule is V-shaped. So if I produce a diagram, we will see here that the hydrogens, delta plus, are towards, as I've drawn it, the top of the diagram, and oxygen delta minus is towards the bottom. There is an unbalanced distribution of charge, and we would conclude, therefore, that the molecule is polar. That is, the dipoles do not cancel. We've got delta plus at the top of the molecule, delta minus at the bottom. It's an unbalanced charge distribution, and therefore the dipoles do not cancel, and therefore the water is a polar molecule. Working from first principles, by which I mean dot and cross diagrams through to shapes of molecules, applying electronegativity difference, come up with an answer to whether ammonia, carbon dioxide, tetrachloromethane, whether these molecules are polar or non-polar. Take your time, think it through, pause the video, come back when you are ready to check your answers. So I'm going to explain the thinking behind whether ammonia is polar or non-polar. So first of all, you need to determine that ammonia is a trigonal pyramidal in shape, and that there's an electronegativity difference between nitrogen and hydrogen, and therefore each bond is polarized. So if we put that into a 3D diagram, we see that the charge within the molecule is not balanced, with delta minus towards the top of the pyramid and delta plus in the corners of the pyramid as I've drawn it. So if I would claim that, therefore, or deduce that there is an unbalanced charge distribution within the molecule. The dipoles, therefore, do not cancel. Just to reiterate, if we draw a trigonal pyramid, we see delta minus at the top, delta plus at my 3 points at the bottom. We can confidently say that ammonia is a polar molecule. So here is my explanation for carbon dioxide. First of all, you need to determine the shape. From the dot and cross diagram, we deduce that the shape is linear. However, we also deduce that carbon, due to the electronegativity difference between carbon and oxygen, that the bonds within the molecule are polarized. So we could represent carbon dioxide as a linear molecule, and delta plus, delta minus, and delta minus. But we can see that the distribution of charge is balanced. To the left we have delta minus, to the right we have delta minus, delta plus in the middle. So we would say that there is distribution, a balanced distribution of charge, that the dipoles, as I've drawn them, cancel each other out, therefore, and that carbon dioxide is non-polar as a molecule. The bonds within carbon dioxide are polar due to the electronegativity difference between carbon and oxygen, but the charge distribution within the molecule means that the dipoles cancel, and carbon dioxide as a molecule is non-polar. Moving on to the last problem. tetrachloromethane. From the dot and cross diagram and applying principles of electron pair repulsion theory, we get that the shape is tetrahedral. Applying the ideas of electronegativity difference, we know that the bonds are polarized. So producing a 3D diagram, we can see that the carbon is central and that the dipole delta minus delta plus, as I've highlighted here, is balanced or cancelled by the dipole delta plus delta minus on the right hand side. The dipole above is balanced by this dipole here. So we have a balanced charge distribution. So the terminology used by the exam board in mark schemes is the dipoles cancel. So I strongly recommend that you use that terminology. The dipoles within the molecule cancel, and therefore tetrachloromethane is a non-polar molecule. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.